Okay, this is the first of three videos to kind of help go through step by step on what a Taylor polynomial is for. Key thing is it is a polynomial. What we're going to do is take things that are not polynomials and create a polynomial that represents the same thing. The example I'm going to use for today, and we're just going to kind of look at the illustration of it and kind of the purpose, is we're going to look at the function sine x. Okay, it can be written as an infinite series of polynomials. Now, this expression and how we get these things here, this expression is not what we're going to learn today. This is just an introduction, but this function is actually equal to the polynomial. Now, if I write this out by plugging in 0, 1, 2, 3, etc., you would get the following function. You'd get x when you plug in 0. Then you would get the second term you would get is actually going to be a 0. But then you get this. The next term you get would be x to the 5th over 5 factorial minus, and the series continues in that form. Notice these are polynomials. Okay, this is a polynomial. You've got x cubed and x to the 5th, creating a polynomial. Now, if you go off to infinity, this polynomial will be exactly the same as the sine x curve. So this polynomial is equal to this function, the sine x curve. Obviously, sine x is not a polynomial. So, since we cannot compute these infinite series, we use part of it to approximate. Key word here is we're going to use it to approximate. And that's what your calculators are not smart. The people that computed them are. What they're using is they're actually using a polynomial, which is a simple connection of multiplications and dividings and add and subtract, simple computations. Using those simple computations, they can approximate sine x for anything you want, sine of 0.1321. The calculator doesn't have it memorized, it actually computes it using a polynomial such as this one. Now, the degree for which you approximate depends on the degree for which the polynomial is. This is referred to P, we refer to this as our polynomial representation for our function. So when I put a little subscript 1, that means I'm only going to use the first order term. So in this polynomial, that's a power of 1, so the only term I have for P1 is x. So that's approximately equal to f of x. But this is like linearization. This is no different because it's a line. It's like using linearization like before. What we did is we create the equation of a line, and we'd use that equation to approximate values with. These are very, very limited because, as you see in the graph, they're only good at very close ranges or near a center, and I'll explain that also. If I wanted to use a better approximation, add another term. In this case, we're using a P3. This number here represents my degree up here. So if I'm using a power of 3 polynomial or order of 3, I'm using that term. So basically I use the polynomial up to that term. So the P3 polynomial would be x subtract x cubed over 3 factorial. Same thing would apply now if I do the 5th ordered polynomial. For my approximation, I would get x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Each one of these are approximations for the function, but each one, as you add an additional order, you're adding a better approximation. We'll see that graphically here in a second. Examples here are coming from, because they're centered around 0, we're not always going to center around 0. They're considered, I have a special name called Maclaurin series. There's a list of them on 491. You're actually going to try to practice writing Taylor series polynomials and checking your answers using that page. So let's look at this graphically real quick. I have graphed the sine curve here. Now, what we're going to do is we're going to look at each one of these approximations separately. The first approximation attempt would be using my first order polynomial, which is a simple line, x. Now, if I graph that line, I get this right here. Y equals x. That's my P1 approximation polynomial. Now, if I use that to approximate, I got values. I have values that around 0 that are very good. So my approximation, if I plug my value into the px, I'm really close. But as I get further out, if I pick a value here at, say, close to pi over 2, my approximation is way off bounds. It's not even close. So it's centered here at 0, but the approximation of polynomial, P1, is very limited. It doesn't go very far, and it certainly doesn't get close enough for me to actually use it for much. Now, if I use a P3 approximator, P3, if I graph the function P3 in my calculator, which you can do also, type this in your calculator, x minus x to the third over 3 factorial. I'll show you how to do that in a second. But when you type that in and you put that in your calculator, you get a third order function. And if I type it in, it goes like this. That's that polynomial. It's a third order polynomial, so you can see it's cubic, but it looks like that. Now, I have added one more term, and if you look, you can see that it actually gets closer here, and maybe even better here. But at pi over 2, I certainly would use this one because it's closer. But the approximation is the P3 is getting actually closer to the sine x curve. Now I want to go one step further. Let's add another term. Let's go to the P5 polynomial. Now it's going to be a fifth order polynomial. It looks something like this. Of course, remember, I'm sketching it, so kind of hides, it disappears, it gets so good, it actually kind of folds in on the curve. So there it is. There's my fifth order polynomial, Taylor polynomial, and as you can see, it's actually, if I use that function, that equation for P5, it's actually a pretty good approximator. It almost falls on top of the curve here. Now, each time I add another term to the polynomial, it gets tighter and tighter. Eventually, if you have an infinite number of terms in your polynomial, it actually falls on top of the sine x curve completely, and it's perfectly the same. Of course, that's if you approach infinity, which we actually can't do. But the point of Taylor series polynomials is the ability to approximate. Okay. Now, just to illustrate, and all we're going to do is illustrate here, is what if I was centered somewhere else besides the 0? And what does that mean? Sorry, I have to move my paper here to make sure my picture looks right. Okay, suppose I want to take this and I actually want to center it around the value pi over 2. So now what I'm doing is I'm going to actually look at up here. There's pi over 2 right there. And then what I'm going to do is I'm going to consider that my center now. My center is right here. Okay, now what I'm going to do is I'm going to create those polynomials. So I'm going to create, in this case, when I do the center around pi over 2, the polynomial is not the same as this one. These polynomials were written based on the fact it was centered at 0. If I rewrote those polynomials and had it centered at pi over 2, they will look different, and their orders are different. So I don't actually have a P1 function. My first one will be a P2 function because it'll be an order of 2 function. And if when we start learning how to write these things, you'll understand why there's not a P1. P2 function is actually parabola, and if I center it around 0, it looks like this. That would be my P2x polynomial, my second order Taylor polynomial. It is actually a very good predictor in the bounds between 0 and pi, but beyond that, it's not very good at all. If I plug in a value, say over here, I'm way off. It's not even close. Okay? Actually, I skipped one. There's actually a P0 function. If I have the P0 function, then let's go backwards here. If I have a P0 is basically, if you have no power, that's a horizontal line. That would be this line right here. The P0 function is actually 1. And if you wrote out the Taylor series polynomial centered around pi over 2, you'd get the first term would be 1, and that's what it would look like. And as you can see, that's not even worth my time using as a predictor. It's okay over here, real near pi over 2, but it's terrible way out here in these ranges out here. Now, and then second order would be this one, which is even better. And then the next one, the way the polynomial works when you write it out, is you get a P4 polynomial, which a fourth order polynomial, which would look like this. And that's your fourth order polynomial. And it has a function. I don't need to write that out for you right now because we don't know how to find those yet. But notice how that is pretty good. It wraps around, it gets real tight. And of course, again, the same thing will hold true. If I go out to an infinite number of terms of the polynomial, it actually will wrap the sine x curve no matter where you center it at. Okay, a couple of the things we kind of want to get an understanding of is the fact is, when we're doing these things, we're creating error. They're approximating equations. They're Taylor polynomials used for approximations. If that's so, then there's an error. Now, how much this will be tested on an AP test, I'm not sure, but I certainly want to make sure that I cover it and help you understand it, because it doesn't make sense to do these things and not understand all the components, at least have semblance. I need my notes on this one here to see. Okay, going back to the centered around 0 polynomial. You first start off with, we have to understand the exact value. The exact value of the function, and our function that I'm noting again is f of x equals sine x. Okay, and if I take sine of pi over 2, I get 1. So this is the actual value of the function. Now, if I use that first order Taylor polynomial and used it to approximate, the function was just x, so it was just pi over 2. Now, if you put that in your calculator, you get approximately 1.5708. Now, you can see that the actual is 1. My approximator using just a one-order polynomial is 1.5708, not very close at all. My second order polynomial, my third order, was x minus x cubed. Again, it's cubed, that's why it's called a third order, 3 factorial. Now, if I use that one and plug in pi over 2, I'll do the work for you, but you get 0.9248. Now, using a third order, look how close that approximator is. I was actually using the polynomial centered around 0, and that's still very close, right around pi over 2. And I'm only using a third order. And imagine using infinite order. It'll give me exactly 1 if I do. Now, fifth order, I won't write that one out, but it was on your previous video, the first part of the video. But this one yields an approximation value of 1.0045. As you can see, that one's even better. Again, the more terms in your Taylor polynomial, the better the approximate it will be. Now, there's basically two types of error that these things create, and one makes sense. The first one obviously makes a lot of sense because your error is just a mistake in your original minus your approximator. So if I look at the P1 only, just to use that as my approximator tool, what I would do is I would compute the error by taking the actual, which we found to be 1, minus the approximation value, which is 1.5708. And again, we talk error, we talk absolute value of it. We don't talk negative error. We say the error is a certain value. And we get the value of 0.5708. So my approximation, my error is this much, quite a bit. Now, Lagrange has a special, it's a special way to compute a very good approximation for error. The reason is because each term you add creates a huge part of the error. Not to mention the fact sometimes we can't actually find the actual value of the function. So I'm going to go back over here real quick and I'm going to look at my Taylor series polynomial. This is the Taylor series polynomial, and I can expand it more using this, but there it is. Now I was just looking at the first order. Okay, so if I'm looking at the first order, my Lagrange error is looking at the very next term. So my P1 ends right there. This is the P1 polynomial. That means I look at the very next term. This term is considered the Lagrange error. It's because this is an easy way for us to compute errors about what the error is without having to compute all of them, because there's infinite parts to that error. All of this is the error for P1. There's P1, the rest, if I don't count it, is counting as error. So this I'm going to call Lagrange. So Lagrange makes it simplest for us to predict an error value. So I'm going to take this term. So for a P1x, my first order polynomial, the very next term is x cubed over 3 factorial. Okay? And if I compute that, I'm going to get approximately 0.6459. Now note the actual error was this. This is the Lagrange error. It's very close. It's not perfect, but certainly it represents a huge part of the error that's actually computed. Now for those people that don't know how to use their calculator to find that factorial thing, that little 3 factorial, let's put this on here and let me show you real quick. Hopefully you can see this. You turn it on. Okay, I'm going to clear my calculator. Now if I want something like 3 factorial, I hit 3. Now to find the factorial, hit the math. Now you need to slide all the way over to probability, PRB, and then down to number 4, which has the exclamation point, which means factorial. Hit that and you get 3 factorial. Hit the button and it shows you 3 factorial. Now remember, 3 factorial means 3 times 2 times 1. Yeah, it's 6. So that's how you can do that in your calculator. Okay, now back to error. Now what I'm going to do is I'm going to switch, and I want to consider now if I had used P3. If I use P3 or my third order polynomial. Okay? The third order polynomial is right there. Was x minus x cubed over 3 factorial. Okay? Its error would be the actual value of the function, which is 1, minus my P3 function with, when I plug it in, I get 0.9248, yielding an error of 0.0752. That means I have an extremely small error. It's not a huge error at all. Okay, it means even with a third order polynomial, it's a lot better than my P1. See the error in my P1? Look at my error in my P3. Okay, imagine how good it would be with a P5. Now, Lagrange is a simple way to find the most of your error, which is the very next term. So if I'm looking at P3, that would be this part. Here's my P3. The very next term is that. That's called my Lagrange error, that component. So what I'm going to do to compute my Lagrange error is I'm only going to look at x to the 5th over 5 factorial. This would represent my error. And that error, my Lagrange error, would equal the value of x. My x here in this case, each time I didn't note what my x is. Each time my x is pi over 2, because that's what I was approximating. I plug in pi over 2 and I get this value of 0.0796. Now look at the two computations of error now. Lagrange is holding the most of the error. The actual error is a little less, but the Lagrange shows a very close resemblance to the actual error. Again, each time you add another polynomial, the error gets better. Okay, there's 3 videos. This was strictly an introduction, kind of give you a feel for error. Don't panic about the error part. It's not a big deal. I don't think so this year. However, it will be next. And there's 2 more videos. The next ones will be helping us write polynomials.